Hello, this script is part of the theory of structure. We are studying about the method of virtual work or the unit load method in the author name. This method is very versatile. It can be used to determine the deformation of the truss, also the beam and the frame. And now we are going to study the analysis of rigid frame as shown here. This frame have the rigid support at A and the rigid joist at B and the free end at C. Under the hypothesis, you may imagine something that since the A is fixed, so when the A is subjected to the load like that, this point gonna deform like this, okay? And at the same time for the beam, when it's subjected to the point load, it's going to deform like this. So in combination of this, we will have the deformation of the frame like this, the first one, and then we may have this one is going to be the fixed, okay? When it's fixed, that means what we have is the V sub A H equal to V sub A V and theta sub A all are 0, okay? And when this one is for the rigid joint, this is rigid joint. What we have for rigid joint is the theta sub B of the beam, okay? Theta here for the beam is equal to theta B for the column. What we are doing is this one is going to defect, for example, to this, and this one gonna have the shape something like this, and this one gonna be the fix, okay? And then when it's alive here, this portion will take the normal angle, 90-degree angle as before, and then this portion will curve like this. And then if this one is the line that's passing the centroid of the frame, okay, and this one move for this, and you may understand that due to the beam have no axial deformation, so this is going to be what this is going to be like 9 millimeter. So this is going to be like 9 millimeter. It's going to be like this, okay? And this one gonna have some deformation, something like this, and this going to be have some curve like this, and this is supposed to be the preliminary deformation of this frame, okay? So in this frame is about 3.5 centimeter, so it's going to be 3.5 centimeter, so it's going to be alive about here, and this is going to be the deformation of this beam, and we may say this is going to be the V sub C horizontal, this is going to be sub C vertical, and also they are supposed to have the slope at this point. This is going to be, this one is the theta sub C. This is a primary graph of the elastic curve, okay? And we will refine this elastic curve after we determine the horizontal deformation, the vertical deformation, and the slope, okay? And what we have is under the method of virtual work, we have the first one that's going to consider is the virtual work equation. Under virtual work equation, what we need to do is, they said, the external virtual work, the external virtual work, virtual work need to be equal to the internal virtual work. So where is the external virtual work? External virtual work you can determine by putting the assumed unit load, okay, to the point that you are looking for the deformation. Now we consider point C. So since the vertical deformation is like this, so we got to put the 1.0 assumed force to be here, and what we have is 1.0 force will times this deformation, so will times this real deformation. Assume force, real deformation, so external virtual work, okay, is external because it's external force, and this is also external deformation, so force times displacement is work, and then it's gonna equal to what have under this applied force, this beam will have the moment inside it. The moment will bend, okay, will bend this frame into the shape like the inelastic shape, and this also will produce the moment, let's call this m sub vertical, okay, and what we have is the 1 unit force produce m vertical, so this one m vertical, and it's gonna time the curve, okay, and we also have the elastic beam theory, in which we have the curvature is equal to m over ei, that is the curvature, and we also have the slope of what? The slope of dv by dx is equal to theta. So we rewrite this equation into the d by dx, and another term there is going to be the dv by dx, and it's going to be equal to m over ei. And now what we have is d theta by dx is m over ei, and then the d theta is equal to m over ei dx. That is the curvature of this beam, okay, the slope of this beam, okay. Actually this one must time d theta, the force time linear displacement, the moment time rotation, and then you got to integrate it. And after you got this equation, you may rewrite this equation to be the form of this. This is going to be equal to integration of the moment due to the unit load time the real slope of the frame, okay, and then we arrive at this equation that can be used to determine the vertical displacement at what? At C, okay. And then if you prefer to find the horizontal displacement, okay, you do again, but this time you're gonna put the force at the point of C again, but this time the unit load gonna be in the direction of V sub CH, Okay, it's going to be 1.2. And I should take a note that, take a note. Okay, elastic curve, drafting the preliminary elastic curve, okay, will help us to specify the unit load. Okay, just take a note on this. This is important. Okay, and also what we have next is, let me have it. Usually this is supposed to have the reaction here, and this reaction also produce related to the constant there. We have this one for a sub x, this one for a sub y, this one for m sub a. Just put it to exemplify the compatibility condition. Okay, next, what we have is this one. What we have is this going to be what? This is going to be 1 point. Okay, unit load, and this unit load gonna time this deformation. So the next equation we have 1.0 and time the horizontal displacement at C. Okay, that is going to be equal to the integration of what? This is going to produce m sub h. Okay, this is going to be the m sub h. M sub h is due to the point load. Okay, so you may put this one for the m sub h. And then again, it's going to time the real slope. That is going to be m dx over ei. Okay, and the last one, we are looking for the slope. So we're going to put what this time? We're gonna put the moment to our frame. Okay, and then this moment gonna be what? Gonna be in the same direction of theta sub c. So to determine this, we put this one as c of 1 point go in the same direction. If you put it in opposite direction, you will get the negative result. So don't worry about it. Everything gonna taken care by itself. So this one gonna produce m sub theta, and what we have is gonna be 1.0 here, gonna time theta sub c, and then it's gonna be equal to, this is external virtual integration of this one m sub theta, and time the slope is going to be m dx over ei. Okay, that is the first step. That's we setting up the concept of method of virtual work or unit load method to the problem we have. So the next step is we're going to determine what? Determine the m, because we going to use a lot of bending moment due to the applied force, and also we got to determine the m sub v to put it here. Okay, and then we got to put what? M sub h to get it here, and the last one we're going to determine m sub theta here to put it here. So next step, we're going to determine the moment equation of m sub v, m sub h, and m sub zeta. You can go it step by step, right? But before we determine the moment equation, we going to set the coordinate of the frame, okay, frame frame segment, okay, segment of what, of BC as x1 and AB as x2. So this is up to you. There is many choice that you can setting up the coordinate, okay. Some may set this is gonna be x1 and this is gonna be x2, okay. But some people said I prefer to set this one as the x1 and setting this one as the x2. It's up to your choice, but you got to determine the best choice, okay. If you use this x1, that means you got to determine the reaction at A, so it won't be convenient, okay. I prefer to select this x1 and x2 better than this x1 and x2, okay. So it's up to you. Everybody have their own choice. By doing that, let me cut this section, okay, and then draw the free body diagram of the frame, and then we determine the equation of that. So this is going to be the first portion of that, and I'm going to put this one also frame. Okay, and what we have is the frame is subjected to the external load. This one is going to be the 10 kilonewton, and this one also subjected 10 kilonewton. You got the free body diagram here, and this is going to be the 10 kilonewton per meter, 10 kilonewton per meter. And what else do we have? You have the x1 here, and you have the x2 here. And then you can determine the moment, and you got to set the rotation of the moment, okay, and following the sign convention. What the sign convention? The sign convention that we have is for the beam, and for the moment it's going to be like this on the left and like this on the right, and the shear is downward here and upward here. This sign convention we use is many times in the engine static. So I put this one as the M1, and if you like to put the shear, you may put the shear here also, okay. And also by the same direction, let me put this one, okay, as the M2. This one may be as the M2, and then I set it for summation of moment equal to 0, and take moment here. The M1 will rotate in the same direction as 10 times x2, so the M1 gonna be equal to minus 10 times, sorry, x1, 10 times x1, and this is going to be our first equation for the M. And then if you prefer, you may take the moment here. We have the shear here also, okay. Summation of the moment equal to 0. Take the moment here. What we have is, this is going to be the resultant force. That is going to be 10 times x2, and it's going to be have the distance x2 divided by 2 here, and we're going to have the M2. This is M2 in this direction. This one also go by the same direction, plus 10x2, and it's gonna time x2 divided by 2. And then if you take this, you have also this 2 meter gonna time 10 kilonewton. So you plus what? Plus 10 times 2 and equal to 0. So by doing that, you got this for 20. This is going to be equal to minus 20. And also this one is a 5 minus 5. And then x2 square. This is going to be the next equation for capital M, the moment due to the applied forces. Okay, and if you like, you may draw this as the table as we have it before. Just put them into the table. For the table, what we can select is the segment. We have the segment. We have two segments here, right? It's going to be the BC and the AB. So just put this one as the BC and another one as the AB. And you may recall the X1, that is BC, gonna be from C to B, from 0 to 2. And for the X2, it's going to be from B to A, that is from 0 to 3. And then the length of this. Okay, it's going to be 0 to 2 for X1 and 0 to 3 for the X2. And then you have the equation for the moment. That is going to be minus 10x1 and then minus 20 minus 5x2 square. And this is going to have kilonewton meter. Okay, if you like to do so, and you may put this one in the green as you get to highlight it, and you don't miss it later. And then what we have is the m sub v. That is the m sub v, m sub h, the m sub h. And the last one is m sub theta. That is m sub theta. And that's what you have it over here, here, and here. Okay, that is going to be the table that's going to help you during your putting the required moment to the virtual work equations. Okay, next we come to virtual work equation. We come to this one, and again, when you put x1 here, x2 here, you gonna put the same here. This one gonna be x1, this one gonna be x2, this is x2, this is gonna be x1. You got to put all of that, okay, into your beam. So let's put this one into your beam, and this is going to be the, okay, and this is going to be the x1, and this is going to be the x1 also, and down here is going to be the x2, and here also it's going to be the x2, and then your frame A, B, C, and your frame is A, B, C, and your frame is going to be A, B, and C. And now you are ready. Okay, when you cut this one, just cut this. So we have this one for the cut. This is going to be the C, and you also have this for 2 meters because your scale is 1 centimeter per 1 meter. So this is going to be 2 meter, so this is 2 meter, and then you're gonna have this one for the x2, and all of them you're gonna have it just project it down here, project this down here, and you may project this one down here also. You're going to have this one, okay, and you are also going to have this one, as you may have for all of them. So you need to follow what you set for the coordinate and also the direction of the moment. All of them must be compatible for each other. Okay, that means you're going to get what you set. So this one is going to be x1, this one going to be x2, and what we have is the first one m sub v. Okay, that is going to be the next step, and you have this one for what? For m sub v1. And actually, if you find the sign convention, you got to capture here. So you got the summation of moment equal to 0. Over here you have 1.0, okay, kilonewton per se. If you like to prefer to set this one kilonewton, and this one gonna be kilonewton meter, to separate between the load of force and the load of moment. Okay, make it clearer if you like. And now if you summation of moment over there is 0, what you have is m sub v1 gonna be, this is going to rotate, okay, about this point in the same direction, so it's gonna be minus 1. It's going to be minus 1 times x1, so minus x1, and then you come over here, okay, and this time this frame is 2 meter, and the moment arm gonna be from here to here, and the m sub v2 summation of moment equal to 0. M sub v2 gonna be equal to, this time is minus of what? Minus 1 times 2, minus 2. Okay, so that is the first set that we get. The one is going to be minus x1, and another one going to be minus 2, and let it go by the yellow. Okay, let's go by the yellow. And next we come to this one, and at our point C we have the 1.0 here, 1.0 here, and what we have is the m sub h, so the same direction that we used before. So this one gonna be in the moment m sub h1, and there is no moment. Okay, so m sub h1 is going to be 0. You just put it summation of moment equal to 0. So this one is 0. And for this one is going to be x1, and this one going to be x2. And what happened is, this direction we will follow it. Okay, and this one, what? This one has the one here, and if you the summation of moment equal to 0, what we have is going to be in the same direction, right? So the m sub h2 is going to be minus x2. Okay, it's going to same direction, and you put across in the opposite of equal sign, and then you get this. So next you get the m sub h1 0. M sub h2 is minus x2, and now you got this for 0 here, and this one for minus x2, and you get the second one. Okay, that's require a lot of consideration, right? You do a lot of practice in the past from in static, so you can do so. And next one, this is gonna be the x2 and this is gonna be the x1. Now the point C is subjected to this 1 kilonewton meter, and this one also 1 kilonewton meter. And again, you use the same sign convention. So this is gonna be the m sub zeta 1, and summation of moment equal to 0. You take the moment here, this is going to rotate in the same direction. So this m sub zeta 1 is going to be minus 1. Okay, and when you take it here also, go by the same direction. And what you have is going to take summation of moment equal to 0. Text over here. Okay, and then what we have is m sub zeta 2 have the same direction equal to minus 1. So we have, or we need to, okay, for the zeta, and this is going to be, put this minus 1, this is going to be minus 1. That is the end of step 2. Determine the moment equations of this one, and this one, and put in your table. Next, we are going to go to the step 3. On the step 3, we determine phi sub phi C, V sub phi H, and zeta sub C by using the virtual work equation, okay, and it's going to require us do a lot of integration because the equation involved with the integration. So the first one, we put the green and the yellow, and then we gonna integrate it. And you should observe that the problem said the beam have different fractional rigidity. Okay, this one is 2i, sorry, this is 2ei, this one only 1 ei. So you got to notice this 2ei, that's ei, and this is 2ei. Okay, if you integrate for the BC, you use this. If you integrate for the AB, you use this. Must be beware of that. Next, let me compute V sub CV. V sub CV gonna be equal to the integration of 0 to 2, and this one times this one, and then it's gonna time minus x1, and then it's going to be the x1, this time divided by only ei. Right. And then you got to integrate it. Next one, 0 to 3, but this time you got for minus 20 minus 5x2 square, and now the x2, and don't forget this one going to divided by 2ei. That is for the column. Okay, and then further integration, this is going to be 10x1 square. So you do the integration, you get 10x1 cube divided by 3ei, and then you get this integration from 0 to 2. Okay, oh sorry, this missed something. This is going to be minus 2. You got to time this with this. Okay, so this is going to be plus 40 minus 2, this plus 10 x2 square. Okay, and then you going to integrate 40 first, so plus, okay, 40 and x1. And now you got to divide it by 2ei. And then you integrate it from what? From 0 to 3. And last one, plus. This time is 10, right? So it's going to be 10. And then x2, you're going to get it for cube divided by 3. And then it's going to have 2ei here. And you integrate this one from 0 to 3. Okay, you have the total of 3 terms. And then this is going to be equal to, like, the first one is 2 power 3 is 8. 8t divided by 3. So this is 8t divided by 3ei. The next one is going to be 120. Okay, and then 120 divided by 2, that is going to be plus 60 divided by ei. And the last one is this one. Cut this one into 5. This one is 27 times 5 divided by 3 plus 135 divided by 3 ei. Okay, if you may put into your calculator, this is gonna be 395 divided by 3, 395 divided by 3. It's going to be 131.67. This is going to be 131.67 divided by ei. And this is going to be downward. Follow the direction of the unit load. Here you got the positive, so that's going to indicate the direction of this. And if you prefer, you may put this one to compute by the ei, and then you got this one for 131.67, and then you divide it by ei. The E is 200 gigapascal. That is 210. Actually, it's 10 power 9 and then 10 power 6 because we have kilonewton in our calculation. Okay, and then kilonewton per square meter. And the I, we have 110 power 6 millimeter power 4. That is 100. And 10 power 6 millimeter power 4 is 10 power 6 meter power 4. And if you push everything, it's going to be cut, okay, and it's going to be divided by 2, so it's going to be 6.58. 6.58. 10 minus 3 meter. Okay, also it can be 6.58 millimeter and down. That is the first one. That's it. This is gonna be 6.58 millimeter downward. And then you do next calculation. This is for the first one. Okay, and a lot of integration, so mathematics is important. Some students may have advantage on the calculator. I recommend you guys to buy the Casio like FX 9000 series, 8000 series, or algebra series. You're going to use it in your future, not just today. And let's have it early, and it will help you to have time to get used to visit. Okay, next we're going to take the second of this. Okay, this equation between the green and the orange to determine the horizontal displacement of C. Okay, that is going to be equal to, and then it's going to be the first thing as before, integration from 0 to 2, and this one is going to be the same thing, minus 10x1 and time 0 dx1 over ei. Okay, this one gone. Okay, it's gonna be 0, and then you're gonna plus this. You're gonna plus this one by the integration, but this time is from 0 to 3, from the 0 to 3, from the 0 to 3 of what of this? That is going to be minus 20 minus 5x2 square, and this one going to be minus x2, and now it's going to be dx2 over this time over the same thing over here over 2ei, and now what we have, minus and minus, this is going to produce 20 x2, and also minus minus plus, this is 5x2 cube. And now if you do the integration of this, you get the first term of 20 x2 power 2 divided by 2, and don't forget about this one, 2ei, and you integrate it from 0 to 3, and then next this is going to be plus 5, and this is going to be x2 power 4 divided by 4. Okay, and don't forget about 2ei, and that's integration from 0 to 3. And now you may have this one cut into 5, so you have 5 times 3 power 2, that is going to be 9 times 5 is going to be 45. So the first one you may get it for 45 over ei, and plus what? Plus this time is 5 and 3 power 4 divided by this is going to be 5 over 4, and 3 power 4, 3 times 3 times 3, 27 times 3, you may get it for 81, and then divided by this is 2ei, that is to be 8. Okay, and then ei. Okay, you got to reduce this. After you reduce this, you may get it for this is 765 divided by 8. $95.625. This is going to be 95.625 divided by ei, and then you get it in this direction. Okay, and if you prefer to do the calculation, this is going to be 95.625, and then divided by same thing, 200 and 200, and this is 100. So it's cut, okay, and then you got this 4.78, 10 minus 3 meter, or you also can get it for 4.78 millimeter, and the direction is going to be in this direction. Okay, now this one we have this one of 4.78 millimeter. Okay, and next, theta sub c. Do the same thing at the theta sub c. At the theta sub c, if you like. Okay, this is the end of this one. That we have the theta sub c. Theta sub c is equal to the same thing. This one gonna be this one and this one. Okay, and then it's gonna be integration from 0 to 2. This time it's going to be this one and this one, minus 10x 1 time minus 1 time minus 1, and then you have this one for dx1 over ei, and then you plus it for the second one, integration from 0 to 3, and this time you have minus 20 minus 5x2 square, and then again you time minus 1, and now you have this for dx2, and then divided by 2ei. Okay, and now this is what? This is gonna be 10x1, and you can do integration of that easily. This one gonna be 20 plus 5x2 square. By follow that, you will get the first term of what? Of 10x1 square divided by 2, and then ei. You do the integration from 0 to 2. Okay, and then next this one plus this one is 20. Okay, you can get it for 20 and time x2, plus this time you're going to divide it by 2ei, and you integrate from 0 to 3, and the last one plus 5x squared 5x2 power 3 divided by 3, and also 2ei, and then you do the integration from 0 to 3. Okay, and then what we have is this is cut. This is going to be 5 times 4 is going to be equal to 20 over ei, and this is cut, this is 10, and you're going to have 3 times 10 plus 30 over ei, and the last one 5 times 3 power 3, 5 times 27, okay, and then divided by 6, and then you may get this one divided by ei, and finally you may get this one for 72.5. So this one gonna be equal to 72.5 divided by ei, and have the rotation in this direction. And if you like to determine the value of it, it's going to be 72.5 divided by, again, 200 and times 100, and then you get this one equal to 3.625 and 10 minus 3 radian. It must be in radian. Okay, it must be in radian. So that is what we have for this. And if you prefer, you may use what you determine and to push all of them onto the scale. Okay, and if you do this, just make this thing like 4. Okay, 1, 2, 3, 4. Okay, 1 meter, 2 meter, this is 4. And this is going to be 6. Okay, this is going to be 1, 2, and 3 meter. And you may have this for this is fixed at A, B, and C, and is subjected to the required force, and also this 10 kilonewton, 10 kilonewton. Okay. Oh, actually it didn't matter, but it's important to put this one at 10 kilonewton here also. Okay, what we have is 6.58, 6.58, about 6.6. okay, if you make it 2 times, it's gonna be about 6.6 is 6.5. About this. Okay, it's gonna be downward here. Okay, this is gonna be 6.612.4, about that. Okay, and this is about 4.8. 4.8 is equal to 9.6 millimeter, about this. So what we have, this is V sub C vertical equal to 6.58 millimeter. This one is what? This one is V sub C H, and it's going to be 4.78 millimeter. And over here, you're going to have the clockwise for 3.625. So this is going to be some kind of 3.625 10 minus 3 radian. Okay, and since this one is moved for 4.75, about 9 millimeter, and you may see this one is going to be about here. This is going to be V sub BH equal to 4.78 millimeter, since the beam, okay, has no axial deformation. Since it's have the same, so it's going to be like that. It's going to be equal to that. Okay, and then what we have is this is going to be the fixed end. This is one move. So when you put this like here, and it's going to arrive here, that is going to be B palm, so it's going to be have the deflection like this. This is going to have what? As you may know, the V sub A H, V sub A V, and 0 sub A all 0. And over here, you also have V sub B V equal to 0, if you like to check. Okay, and the last one. This one must taking care of their perpendicular. Okay, even though it's alive here, this must be keep itself as the normal angle. Okay, and this portion of the beam will defect. Like this. And when it's alive here, that is going to be C palm. This is going to be B palm. This is going to be the elastic curve, okay, of this beam. Elastic curve of this beam. And if you prefer, you have the equation of the deformation, right? You also may be able to draw the moment diagram of this beam. 1, 2, 3, and 4 if you like. And you prefer, you may put this a little bit here. Okay, and then what you have for the equation? The first one, 10x1. So if this is x1 start here, this is going to be 0. And for 1 meter here, that is minus 10. So it's going to be like minus 10. Minus 10 here. For 2, it's going to be minus 20. It's going to be linear. And this is going to be minus 20. And then for x, we start from here. If x 0, it's going to be minus 20. Minus 20. And if you prefer go by 1 meter, 2 meter, and 3 meter, follow this for 1 meter. That is going to be minus 20, minus 5, minus 25. 10, 20. This one. Minus 25. If it's 2, it's going to be 5 times 2 square. That is 40. That is minus 20 and minus 40. 1, 2, 3, 4. Minus 40. And if it's 3, that is 29 times 5, 45. And then it's going to be 65. 20, 40, 60, and then about this, that's this, minus 65. So you can draw the moment diagram of this frame like this. And it's going to be, see, follow this. Since this is negative moment, okay, this is also the negative moment. When it's negative moment, the curve going to be like this. And it's going to be like this. So it's corresponding to our curve here and our curve here. Okay. And the last thing, if you prefer, you may draw the reinforcement. This is the M diagram. If you like, just put it 1, 2, 3, and 4. And then you may put this 1, 1, 2, 3, 4, 5, 6. And what we have, if this one is the reinforced concrete beam, you also can use the moment diagram and elastic curve to find the pattern of the reinforcement. Usually we have reinforcement like this for the beam, but for the frame. But when the subjected to moment like this, we always put the reinforcement on the tension portion. So extra reinforcement must be put. Oops, sorry. in this direction and also in this portion of the beam. So this is the reinforcement pattern. Okay, and that's all we can do for this problem. We can draw the elastic curve, we can draw the moment diagram, or even we can put the reinforcement pattern that's corresponding to our moment diagram and our elastic curve. Okay, so let's show you, demonstrate to you how we solve for the displacement of the frames, including the vertical displacement and the horizontal displacement and the slope. Okay, this frame we are interested at the point C, and we use the virtual work equation. Okay, following the method of virtual work, we can solve this equation, this frame effectively, and hope you guys trying to understand it. And we will have some more pattern of the frames that we will working on, and I will come and show you later. Okay, that's it for this clips. Hope you enjoy the study. Bye bye.